Hello viewers, welcome to this lecture on control systems. In this lecture we will see some formulation of certain control systems or in other words some mathematical models of some practical control systems. In previous lectures you might have studied various dynamical systems. So, the definition of a dynamical system is a system which evolves in time and changes according to a known function of t is time as well as the current state of the system. So, such systems are called dynamical system. So, for example, earlier we have seen the population dynamics. So, it is of the form let us say dx by dt is some alpha times x of t. So, it is a simple model of a population dynamics where x of t represent the population of a species at a time t and how it changes, the rate of change of the population dx by dt is proportional to the population at time t. So, alpha times x of t is the simple mathematical model which have been analyzed, or improved model of the population dynamics is it is something like alpha x minus beta x square. So, this represent it is called the logistic model of the population growth, and so here also the rate of change of the population x is proportional to x itself and x square, a combination of x and x square is given. So, it is it is in detail you have studied earlier about this population growth. So, these are called the dynamical systems. In general, if there are more variables of the state, so let us say x1 of t, x2 of t, xn of t are the n state variables, then in equation 1 we have a model dxi by dt, the rate of change of the state xi is equal to a function fi of all the states x1, x2, xn and the time. So, this n equation together, n first order differential equation together is called a dynamical system, and it may be linear or non-linear depending on the function fi. If all the functions fi are linear functions of the variables x1, x2, xn, then it is called a linear system, otherwise it is a non-linear dynamical system. This x1, x2, xn are called the state of the system, etc. So, in the vector form we can write if x is x1, x2, xn vector, then we can write the equation 1 as dx by dt is f of x comma t, where f is a vector f1, f2, fn, the n functions in the right hand side. So, it is called a dynamical system and the state space here is Rn. So, in this equation there is no external force or external input in the system, because the system is evolving on its own. The current state x of t itself acts as the input for the evolution of the x of t for the future time. But if you include an external input in the system which will affect the evolution of the system, then it is called a control system. So, here we can see that x1, x2, xn are the state of the system and u1, u2, um functions of t are the control of the system. So, for example, if we consider the equation dx by dt is some alpha times x minus let us say x naught. So, here x of t is the temperature at time t. Any substance which is kept in the room temperature, let us say x naught is the room temperature, and this is alpha times minus alpha times. So, the rate of change of the temperature of a substance which is kept in the room temperature is alpha times minus alpha times x minus x naught, where x naught is the room temperature and x is the current temperature at time t. So, it will behave in this particular way. It is a simple mathematical model of the rate of change of the temperature of a substance. So, here this is simply a dynamical system, because it is only a function of x, the right hand side, but if we include some external heating system for the same problem. So, this is say u of t is included, then the external heating will also affect the temperature of the substance. So, this is a control term u of t. So, it becomes a control system in this case. So, the evolution of the temperature as a function of time will be affected by this control term u of t. So, this is called a control system. So, here we write a control system in the equation 2, dxi by dt is fi of x1 x2 xn and u1 u2 um and t, the n equations I equal to 1 to n, and u of t, that is u1 u2 um of t, it belongs to this control space Rm here. So, this equation can be written as dx by dt is f of x comma u comma t in the vector form, and if t is explicitly present in the equation like f of x comma u comma t, then it is called the time varying system. Time invariant system means the functions are f is a function of x and u, but u and x and u are function of t, but in the equation t is not appearing explicitly. So, this is called the time invariant system. So, time invariant system, it does not mean that the system does not change with respect to time, it changes, but in the model, the mathematical model, t does not appear explicitly. The rate of change of the variable x is not directly affected by t, but as a function of x and u, it is changing with respect to time. So, such system are called time invariant system. So, for example, of a time invariant system, we see this one dx1 by dt equal to minus a x1 plus b x1 x2, dx2 by dt is minus c x1 x2 plus d x2, a b c d are positive constants. So, this is a system where x means x1 x2, this is the state of the system, and the right hand side are the two function of the state variables. So, this is a familiar prey predator model. It is a dynamical system because there is no external control available in this equation. So, here x1 is the predator population. Predator population at time t, and x2 of t is the prey population. So, the rate at which the predator changes, the population changes is the minus sign represent that in the absence of any prey the population will decrease, because the food for the x1 prey. So, in the absence of x2, x1 will decrease, but in the presence of x2 the population x1 will increase. So, the ratio in which it will increase is its own population. So, b times x1 is the ratio in which the population, sorry, b times x2, more and more availability of x2 will increase the population of x1. So, b into x2 is the ratio in which x1 will increase. So, that is a plus sign, and dx2 by dt here in the absence of the prey, in the absence of the predator, the x2 population will increase on its own, and in the presence of the predator the population of x2 will decrease. So, how it will decrease? If x1 is of a bigger size, then c times x1 will be a bigger size. So, the rate of decrease of x2 will be proportional to c times x1 of x2, that is the rate of decrease, and this is the rate of increasing. So, this represents the prey predator equation. It is a dynamical system. Now, if we artificially increase the population of the prey so that the predator population is maintained, so we can use some methodology for increasing the population, the prey population x2 population by a term alpha times u of t. So, this is some population control method is applied on x2, then it becomes a control system. So, this can be either x2 can be increased or decreased by the population control. If you want to decrease the population of x1, the rate of change of x2 can be decreased by a control u, so that x1 also decreases. So, the controlling the population by a control term, this is a control system, and time invariant, this both the systems are time invariant system, because there is no t appearing explicitly in the equations. So, now we will consider an important problem, that is the inverted pendulum. So, the inverted pendulum is like this: we have a cart which will with less, there is no friction, it will be moving freely, and the inverted pendulum is attached at the point O here. So, it will, this is the fixed position. So, this will move like this. So, if it is not stable, it will fall down. So, the problem is to keep this inverted pendulum in a vertical position by adding a controlling this one, by controlling a u of t is given the control, so that if it falls down in this right side, then it will be pushed to the right side, so that it will come to the vertical position. If it falls in the left side, then it will be pulled back, so that the pendulum will be again kept in the vertical position. So, the aim is to just keep it in the vertical position, that is a stable position, but it is a highly unstable position. A small disturbance will make the pendulum fall down. So, it should be controlled by this control u of t. So, how to formulate the equation? So, let us say that the length of this is 2L, okay, and the center of the length is 2L, the center of mass is there, m is the mass of the pendulum and capital M is the mass of the cart on which the pendulum is positioned, and let us say Z is the displacement in the horizontal direction. So, we can formulate the displacement in the horizontal position is Z, and now at a particular position the angle is theta, let us say, then this L sin theta is, so we will be watching the movement of the center of mass. So, we will say that L sin theta is the horizontal motion and L cos theta is the vertical motion of the center of mass. So, vertical position at any angle theta is L cos theta and L sin theta is the horizontal movement. Now, if you differentiate it 2 times, the displacement, differentiate the displacement 2 times, we will get the acceleration in that direction. So, we will formulate the equation of motion of this pendulum in the following way. So, let us consider the 4 variables theta, and theta is the angle, theta dot angular velocity, z is the displacement in the horizontal direction, z dot is the velocity in the horizontal. So, we call the 4 variables as x1, x2, x3, x4. The mass of the pendulum is small m, mass of the carriage, the cart is capital M. Now, we can see that in the x direction, this direction, this is the pendulum and this is the x direction. In that direction, the force in the x direction due to the pendulum is, because the L, this is L sin theta, this position, and L cos theta is the movement of the center of mass is L sin theta, and if you take the second derivative of L sin theta, that gives the acceleration in the x direction, then mass into acceleration will give the force x1 in the x direction of the force in the x direction. Similarly, in the y direction, L cos theta is the displacement in the y direction. So, second derivative mass into the second derivative give the y1. Now, the force in the direction due to the cart motion, the cart is moving in the x direction. So, z is the displacement, the second derivative will give the acceleration. The mass is mass of the cart plus the pendulum, together it gives m plus capital M into z double dot is the force due to the cart motion, the carriage motion. So, the control to be balanced, it is these 2 forces, x1 force and the x2 force. So, u equal to x1 plus x2 is the control action. So, that is what we have in this previous picture, u of t is the control. So, it should balance the 2 x direction forces only, because y force is in the vertical direction, this control u should balance the x direction. So, we have u is equal to x1 plus x2. Now, the horizontal force is given by this expression. Due to the pendulum only, we will get the x1 part m into d square by dt square of L sin theta plus m into z dot, because only m force we are measuring here. Due to the pendulum, we have the x direction force which is exerted at the point O, because the mass capital M is below that O position. So, whatever is in the above, the force exerted at this point O is given by equation 7, and equation 8 it gives the vertical force by the pendulum is y equal to y1. Now, in the equation 8 we have the inertia into the acceleration theta double dot is the torque. So, the torque exerted by the pendulum is given by the y force into sin theta. So, we have to measure the torque like this. So, this is the pendulum center of mass here. So, the force exerted by in the y direction and force exerted in the x direction. So, this is the x force and y force at the center of mass. So, this it will give a torque like this. If you resolve it in the perpendicular direction, so this angle, this is theta, and so this is 90 minus theta. So, x into cos theta will be the force exerted in the vertical direction to the pendulum, that is x cos theta, and it will give a torque because it is pulling it downwards in this direction. The torque direction will be in this way. This is the vertical. So, the torque exerted by the x force is minus, because this is the y direction, this is the x direction, the torque is in the negative direction. So, we get a minus sign x cos theta is the torque due to the x force. Similarly, y is this and the vertical direction to this is y cos theta, sorry y sin theta is this expression, and this will exert a positive torque here. So, we get a positive sign y sin theta and minus x cos theta is this one. So, this is the theta angle, sorry this is x cos theta and a negative sign, and y sin theta with a positive sign multiplied by the length will give the torque exerted at this point O. So, from this equation, the previous equation, we get from this equation 6, that is u equal to x1 plus x2, x1 is given by 3 and x2 is given by 5. So, summing this 2, we get this equation m plus capital M z double dot plus this expression equal to u. Now, exactly we will calculate this y and x. Capital Y is given by this expression as mentioned in the previous slide. We substitute this, and expanding d square by dt square of this expression will give this one, and capital X by using the same expression in the previous slide, we get the expression as given in the last line, can be calculated. Now, the balancing of torque, the torque is the inertia into the angular acceleration, and the right hand side from the previous step, if you collect the sin theta cos theta coefficient, we will get this expression theta double dot multiplied by this term because we take theta double dot, all the theta double dot to the left side. So, we will get this expression. First term is 1 by 3 m L square, and from here we get m L square cos theta and here we get m L square sin theta sin square theta, because we have to multiply from this one. Okay. Here we get m L square sin square theta with a minus sign. When it comes to the left side, we will get this one and this expression. So, the remaining expressions are in the right hand side. So, ultimately simplifying this equation, we get theta double dot, and this whole bracket will become 4 by 3, and the right hand side is given as it is. So, the equation 11 is the equation of motion, and the control equation is given by this expression. Now, equation 9, if we take and then simplify that expressions, the second derivative expressions, we will get u is given by this one, this expression in terms of theta double dot and z double dot, etc. So, ultimately what we get is the equation 4 by 3 theta double dot m g L theta minus m L z double dot, that is one equation. Another is u is equal to m L theta double dot minus m L theta into theta dot plus m into capital M z double dot. This is due to this expression. So, we will replace sin theta approximately equal to theta and cos theta is approximately equal to 1. So, when we substitute these expressions in the previous two equations, equation 11 and 12. So, wherever sin theta is there, we will put theta and cos theta to be 1, and in all the expressions we get these two equations. Now, for a specific case, if the mass of the pendulum is 1 unit and mass of the cart is 9 unit and the length of the pendulum is 2 unit. So, the half of the length is 1, capital L is half length, it is 1, then we get the equation to be like this, these two equation. By substituting the m, L and capital M values, we get this equation. Now, when the pendulum is in the vertical position and if it is disturbed slightly, so theta is small, the assumption theta is small, it means that from the vertical position it is slightly disturbed, the theta value is not deviating too much. Similarly, the velocity, it is moving with a very slow velocity because already it is near the vertical position. So, velocity as well as the angle theta, both are the angular velocity and angle theta, both are very small. So, we can also neglect this theta into theta dot, the both of them are negligible values. So, we can neglect it. So, the equation finally becomes like this, 4 by 3 theta double dot minus g theta plus z double dot equal to 0 and theta double dot plus 10 z double dot minus u equal to 0, these two equation. So, we get the equation in this particular form, and now if we write the variables, x1 is theta, x2 is theta dot, x3 is z, x4 is z dot. So, the relation is x1 dot equal to x2, and from the equation 4 by 3 x2 dot, this theta double dot minus g x1 and z x double dot is this one. So, it should be plus sign here, sorry, 4 by 3. So, we get this equation equal to g x1 and x3 dot is x4 and here x4 dot, that is 10 x4 dot is this and x2 dot is this one equal to u. So, this two equation we get. From here we can write it in the form of a matrix, the expression 4 by 3 1 1 10. These are the coefficient of the matrix x 2 dot x 4 dot. So, that is in the right hand side x 1 g and minus u from the previous equation. So, now we can calculate the values of x 2 dot x 4 dot by taking the inverse of the matrix in the left hand side. So, the inverse is given by this expression into this. So, directly we can get the values of the x 2 dot in terms of x 1 and u, similarly x 4 dot in terms of x 1 and u. Now, so from here we can easily see that x 1 dot is 1 into x 2 and x 2 dot is from this equation. So, it is 30 by 37 into 37 g into x 1, okay, and minus 3 by 37 into minus u, therefore, it is plus 3 by 37 into u. So, that is x 2 dot equation, and x 3 dot is x 4. So, we have 1 into x 4, x 4 dot is from this equation again. So, minus 3 by 37 g into x 1 and 12 by 37 into minus u. So, this expression is given. So, we can write this equation as x dot the left hand side equal to a into x into b u. So, it is a standard form of a control system. It is a time invariant linear system, linear control system, this formulation. Similarly, when the pendulum is in motion, if the angle can be measured, because we are interested in making the pendulum to a vertical position, that is stabilizing the pendulum position as a vertical position. So, it is important to know at what angle it is there at each instant of time. So, if you are able to measure the angle at each instant of time, then the observation means we are measuring theta of t. So, if the observation of this experiment is the angle theta, then it can be written as 1 into theta. So, y the observation equal to C matrix is 1 0 0 0 into the theta dot z dot, we get the observation to be equal to theta. So, we have the equation, linear equation and the observation equation like this. So, this is the formulation of a simple the control system, the control system of the inverted pendulum. Okay. So, for this because it is an important problem in the mechanics, various concepts like the controllability, observability and stability of this particular control system is analyzed extensively in the control theory courses. So, we can study this as an example in various concepts in the coming lectures on the controllability, observability, etc. Thank you.